Welcome back. In the last lecture, we talked about the difference between and or. So front page here, I'm going to do a brief review of the difference between and or, and then we'll add on. We have a table here. These are people from 3 different cities and their preferred mode of transportation. Part A, if one person is selected, find a probability that the person prefers travel by plane. Probability is going to be a fraction. We're talking about picking people here. So for the bottom, how many different people could I pick? That's really just asking for how many people are there total. So let's add up these numbers. Six plus 15 plus 12 plus 5 plus 9 plus 10 plus 0 plus 6 plus 17. 80. Okay, 80 people total, so that's 80 people that I could pick from. That's the bottom. For the top, I want the people who prefer travel by plane. So how many people prefer travel by plane? These 12, these 10, and these 17. So 12 plus 10 plus 17. 39. Part B. If one person is selected, find a probability that the person is from Los Angeles and prefers travel by plane. Keyword here is the word and. Okay, bottom is still going to be everybody, which is 80. Up top, I want people from Los Angeles and prefer travel by plane. And the word and, remember, means at the same time. So I want the people who are from LA and at the same time they like plane. And as a tip, it should just be a single box or a single number. So LA plane. LA plane. So these 17 people are from LA and at the same time they like plane. 17. Part C. If one person is selected, find a probability that the person is from San Francisco or prefers travel by train. Keyword here is the word or. The bottom, same as before, is going to be the total, which is 80. Up top, San Francisco or train. Okay, so or means I'm going to take the San Francisco people, the train people, and combine them and get a bigger set. And the way I usually do this is I'll take my San Francisco numbers, which are 5, 9, and 10. And then I'll add on the train numbers, which is 15. The 9, I'm not going to write again, okay, because I already got the 9 when I did the San Francisco numbers, so just the 15 and the 6. Okay, so in addition, plus 15, plus 6. Bottom is still 80. Up top, 5 plus 9 plus 10. Plus 15 plus 6. That's 45. Part D, if one person is selected, find a probability that the person's favorite mode of transportation is not car. Okay, bottom is going to be everybody, which is 80. Okay, not car. Not car would be all the trains and all the planes. So 15, 9, 6. And then 12, 10, 17. 69. Today we're going to talk about three new concepts. The first of which is called conditional probability. And this is the symbol for conditional probability. And what it means is it's the probability of A The vertical line stands for the word given. That B already occurred. Another way you can read this is probability of A given that we have additional information B. Once again, this vertical line stands for the word given. And that's the key word you'll be looking for. All right, so let's see how we compute conditional probability with an example. Part E. If one person is selected, find a probability that the person prefers travel by car, given that the person is from San Francisco. Keyword I see here is the word given. And that indicates that this is going to be a conditional probability. For conditional probability questions, I do recommend using the symbol or the correct notation. So what we're looking for here is probability that the person prefers travel by car. So probability of car given, which is the vertical line, that the person is from San Francisco. So car given San Francisco. And the way you compute this, so let me back up a bit. Every question we've looked at so far, the bottom has been everybody, right? The bottom has always been the total. So anytime you see the word given and you're working with conditional probability, the bottom is not going to be the total anymore, okay? So we're looking for probability that the person prefers travel by car, given that we have additional information that the person is from San Francisco. Because we have additional information that the person is from San Francisco, we're just going to focus on the San Francisco numbers for the top and the bottom. And that's because we know we have additional information that the person is for sure from San Francisco. So we're just going to focus on the San Francisco numbers for the top and the bottom. So for the bottom, focusing just on the San Francisco numbers, how many are there total? Just the San Francisco numbers would be 5, 9, 10. So 5 plus 9 plus 10. The total is 24, so that's the bottom. And then still just focusing on the San Francisco numbers, how many prefer car? So just the San Francisco numbers, how many prefer car? 5. Okay, and that's it. Let's try another one. Part F. If one person is selected, find a probability that the person is from San Francisco, given that the person prefers travel by car. So once again, I see the word given. In symbols, I'm looking for San Francisco given, so that's San Francisco given car. Okay, anytime you have conditional probability, the given part, which is the second part, is going to tell you what to focus on. So we're focusing on car for the top and the bottom. Okay, start with the bottom. Focusing just on car, how many are there total? So just on car, that would be 650. That's 11. That's the bottom. And then for the top, still focusing just on car, how many are from San Francisco? So just on focusing on car, how many are San Francisco? 5. Okay, so the point I want to make with part E and F is that car given San Francisco, and then the other way around, San Francisco given car, notice that you get different answers. Okay, so the order here does matter. All right, one more example, part G. If one person is selected, find a probability that the person is from Los Angeles, given that the person prefers travel by train. So once again, I see the word given. Okay, in symbols, I want Los Angeles, so LA, given train. So what numbers should I focus on here? Okay, we're focusing on the given part, which is the second part. So we should be focusing on train for the top and the bottom. So for the bottom, focusing just on train numbers, how many are there total? So just train numbers, 1596. What's 1596? 15 plus 9 plus 6. It's 30. Okay, so focusing just on the train numbers, the total is 30. And then still focusing just on the train numbers, how many are LA? Just train numbers, how many are LA? 6. The second new thing we're going to talk about is called the multiplication rule for probabilities. I'm going to write down a formula, but don't worry about this formula too much. So the multiplication rule for probabilities is a formula for calculating probability of A. I'm going to write and then B. And the way you calculate probability of A and then B is probability of A, probability of B given A, and then you multiply. That's why it's called the multiplication rule. So this basically says that to find the probability of A and then B, you can kind of do it separately. You do A, and then you do B, given additional information that A already occurred, and then the key point here is that you multiply. So don't worry about the formula too much. I'm going to show you how to use this formula in an example. So part H. If two people are randomly selected, what is the probability that the first person prefers travel by plane and the second person also prefers travel by plane? All right. So up to now, every question we've looked at has said if one person is selected. The new thing for on this page is that we are selecting two people, three people, so multiple people. And the way we're going to use this multiplication rule is to select two people. One way you can do that is to select one person and then select a second person. And what this is telling me to do is we can do it separately and then just multiply the two fractions. All right, so I'm selecting two people, which means I'll need two fractions. And let me write down what the first person is and what the second person is. First person, I want to be prefers travel by plane. So first person is plane. The second person also prefers travel by plane. So second person is also plane. Okay. The first fraction is just like a regular probability question that we've talked about before. So for the first fraction, the bottom is going to be everybody. So that's 80. Is it 80? Yeah, it's 80. And then for the top, I want how many plane people. So plane would be 12, 10, 17. What's 12, 10, 17? 39. Okay, so that's the first person, right? First person prefers probably the first person prefer travel by plane. Now for the second person, this is where we have to take into account that the first person was already picked. Okay, so for the second fraction, the bottom, if we take into account that we already picked one person for the first slot, we don't have the full 80 anymore, right? We have one less person, so we're down to 79. And then for the top, I want the plane people. Okay, we also have to take into account that we also already picked the plane person for the first slot, so I don't have the full. So 12, 10, 17 is 39. I don't have the full 39 because I already used one plane person for the first slot, which means I'm down by 1 to 38. Okay, and that's how you use this multiplication rule. All right, so let's try a couple more examples. Part I. If two people are randomly selected, okay, that already tells me that I need two fractions. What is the probability that the first person is a person from LA who prefers travel by train? Okay, so first person is LA who prefers travel by train. So LA train. Second person is from San Francisco. Okay, first fraction, the bottom is going to be everybody, which was 80. For the top, I want LA train people. So LA train, 6. Okay, second person, for the bottom, I already chose one person, so I should be down by 1 to 79. For the top, San Francisco. San Francisco would be 5, 9, 10. 5, 9, 10 is 24, I think. Okay, 24. Now, is it 24 or do we have to reduce it by 1 like in part H to 23? So in the part H, the reason why I had to reduce is because I used a plain person in the first slot, right? But here, I haven't used any San Francisco people yet, right? The first slot was LA train. So I don't have to reduce it by 1 because I haven't used any San Francisco numbers yet. So I should have the full, what do we say it was? 24. Okay, make sure you understand why in part H I had to reduce, and in part I did not have to reduce. Okay, so in part I, the second slot was San Francisco, and if we look at the first slot, we didn't use any San Francisco numbers. In part H, the second slot is plain. If we look back, we did use plain already, so I had to reduce by 1. Part J, if 3 people are randomly selected, so already I know I should have 3 fractions that are multiplied together. What's the probability that the first person is a person from San Francisco who prefers travel by plane? Okay, first person is going to be San Francisco plane. The second person is a person from Los Angeles who prefers travel by plane. So second person is LA plane. The third person prefers travel by plane. So third person is plane, no city attached. The first fraction is going to be, the bottom is going to be everybody, which is 80. Up top, I want SF plane. How many SF plane? SF plane, 10. Second fraction, okay, because I chose one person already, the bottom is going to be down by 1 to 79. And let's go ahead and do the bottom of the third fraction. Down by 1 again, 78. Right. The second fraction here, I want LA plane. So LA plane would be 6. Now the question is it 6 or do I have to reduce by 1? So LA plane, if we look back to the first lot, did I use LA plane yet? I have not, right? I used SF plane, but I haven't used exactly LA plane yet. So I should have the full 6. Third fraction is just plane, no city attached. So plane would be 12, 10, 17. So 12, 10, 17. One second. LA plane is not 6. LA plane is 17. So LA plane is 17. Third fraction, plane. So plane, no city would be all the planes. So 12, 10, 17. So 12 plus 10 plus 17. That's 39. Okay, 39. Or do we have to reduce? So have we used plane numbers? We did, right? I used the plane here and I used the plane here. So we actually used 2 planes already, which means I should be down by 2. So the total was 39. So down by 2, this would be 37. Okay, so make sure you understand why it's 37 and not 39. Part K. If 3 people are randomly selected, so I know it's going to be 3 fractions, what is the probability that the first person is a person from Sacramento who prefers travel by car? So first person is Sacramento car. Sac car. Second person is a person from LA who prefers travel by train. So LA train. Third person prefers travel by car. So car with no specific city. First fraction, bottom is going to be everybody. So that's going to be 80. Sac car. Sacramento car. Sacramento car, 6. Second fraction, The bottom I should be down by 1, which is 79, and then let's do the third fraction. I should be down by 1 again for the bottom. That's 78. Second fraction, LA train. LA train would be LA train 6. I forgot to talk through that. Is it 6 or do I have to reduce by 1? So did I use any LA train yet? No, right? First slot was sat car. So I haven't used any LA train yet, which means I should have the full 6. Last fraction, car. Car is 650. That's 11. Is it 11 or do I have to reduce? And the question you should ask is, have you used any car yet? I have. I used 1 car, right? So I should be down by 1 to 10. So make sure you understand why it's 10 and not 11. And also make sure you understand why part K, for the last slot, I reduced by 1, whereas for J, the last slot, I had to reduce by 2, from 39 to 37. In J, I used 2 planes already, which is why I reduced by 2. In K, I only used 1 car, which means I reduced by 1. The third new concept we're going to talk about today is solving at least 1 problems. Before I talk about solving at least 1 problems, I have to talk about complement. Complements we talked about already when we talked about set theory. So in set theory, the complement of a set are all the things that are not in that set. And for probability, it's going to be something similar. Say I have an event E, and E stands for it rains today. What would be the complement of E? The symbol for complement is the same one we use for sets. It's going to be E with a superscript of C. If E means it rains today, then E complement means it does not rain today. And now let's talk about some probability. Say I know that the probability of it raining today is 0.2. And that's as a decimal. If you prefer percents, 0.2 as a percent would be move the decimal 2 to the right. It'd be 20%. So if you know that the probability of it raining today is 20%, what's the probability of it not raining? So if you know the probability of it raining today is 20%, the probability of it not raining would be the rest, which is 80%. And what math did we do to get this 80%? We took 20%, right, and did 100% minus 20% is 80%, right? That's in percent form. In decimal form, what you would do is you would take 100% as a decimal would be 1, minus the 20% as a decimal will be 0.2, and you'll get 0.8, okay, which is 80% in decimal form. So the point here is that if I know the probability of E, the probability of E complement is going to be 1 minus the probability of regular E. Okay, so we'll need that idea. The probability of the complement is 1 minus the probability of regular E. And it also works the other way around. The probability of regular E is 1 minus the probability of the complement. All right, at least 1 problems. Let's actually read part L. If 3 people are randomly selected, find a probability of at least 1 person, that at least 1 person is from Sacramento. What does at least 1 mean? We're talking about selecting 3 people, so at least 1 means 1 or more. So it could mean 1, it could mean 2, it could mean 3. And that's the problem with solving at least 1 problems directly, because it could mean 1, it could mean 2, it could mean 3 in this case, which means you have to take into account each of those situations separately and then combine the answers. So instead of solving at least 1 problems directly, We're going to do it by looking at the complements because it's easier. So what is the complement of at least one? Okay, so let me use an example to help you figure out what the complement is. I'm going to write down some numbers. 0, 1, 2, 3, 4, 5, 6. Which of those numbers are at least 1? At least 1 means 1 or more. So 1, 2, 3, 4, 5, 6, and so on. All of those numbers are at least 1. Okay, which means if you're solving at least one problem directly, you would have to take into account 1, 2, 3, 4, 5, 6, all of those things, and then combine your answers. What is the complement? What number is not underlined in red? 0. Okay, so the complement of at least 1 is 0. I'm going to write none. All right, so now we're ready to write down the main idea. So the main idea here is that to find the probability of at least 1, we're not going to do it directly because that's hard. So instead of finding the probability of at least 1, I'm going to do 1 minus the probability of the complement, which is none. And this is the idea we're going to use on any problem that says at least 1. All right, so let's try an example. Part L. If 3 people are randomly selected, find a probability that at least 1 person is from Sacramento. So keyword is at least 1. I'm looking for at least 1 Sac. Which is going to be the same thing as doing 1 minus the probability of none from Sac. So I'm going to write none Sac. So instead of doing at least 1 directly, we're going to do the right side, which is 1 minus the probability that none of them are from Sac. So 1 minus. Now, we're talking about 3 people, so I'm going to need 3 fractions here for the none-Sac part. I'm selecting 3 people. What does it mean for none of them to be from Sac? That means that first person is not from Sac, second person is not from Sac, third person is not from Sac. So all 3 are not from Sac. So not Sac. And then you'll just find the fractions for not Sac, not Sac, not Sac. So once again, 3 people, none of them from Sac means that not Sac, not Sac, not Sac. All right, so first fraction, the bottoms should be everybody. Everybody was what? Everybody's 80. And then let's actually fill the bottom for the other fraction. So 80, and then the second person, because we chose 1 person already, that's going to reduce down to 79, and then 78. Okay. First fraction top, I want not Sac. So how many not Sac? Not Sac would be 5, 9, 10. Plus 0 plus 6 plus 17. 47. Second person, I also want to be not Sac. And because I already chose 1 person not Sac already, for the second blank, I should be down by 1 to 46. And then down again to 45. And so the answer you're going to enter is going to be that. So make sure don't forget the 1 minus. So 1 minus 47 over 80 times 46 over 79 times 45 over 78. Part M. If 3 people are randomly selected, find a probability that at least 1, so once again I see the word at least 1 person prefers travel by train. Okay, I'm looking for probability at least one train. And the way we're going to do at least one is we're going to do 1 minus none. None train. So this is 1 minus. We're talking about 3 people. So 3 fractions. Okay. 3 people, none of them train, means not train, not train, not train. First fraction, the bottom is going to be everybody, which was 80. And then it goes down, right? 80, 79, 78. Now, first fraction, I went not train. How many not train? Not train would be the cars, 650. And then the planes, 12, 10, 17. 650, 12, 10, 17. That's 50. Second fraction, I also want to be not train, which means I have to reduce by 1 because I used not train already. So we're down to 49 and then 48. Okay, so keep in mind that even though we're looking for probability of at least one train, on the right side, for the fractions, we're looking at not train, not train, not train. That's because we have this 1 minus, so it's 1 minus the complement. That's why, even though we're looking for train, you're actually doing not trains. N. If 3 people are randomly selected, find a probability that all 3 prefer travel by plane. Now, I threw this one in just to point out that you're only doing 1 minus none when you have at least 1 problems. For N, I don't see the word at least 1 anywhere, right? If 3 people are randomly selected, find a probability that all 3 prefer travel by plane. I don't see the word at least 1. So if you don't see the word at least 1, then you do it the regular way. So 3 people, 3 fractions. I want all 3 planes, so plane, plane, plane. And you do this the same way you did it on the previous page. So the bottom for the first fraction will be everybody, which is 80. It's going to go down to 79, 78. First fraction, I want plane. Plane is 12, 10, 17. Pretty sure that's 39. And then another plane. So that means I should be down by 1 to 38. And then again, another plane to 37. All right, so we just got done talking about conditional probability, multiplication rule, and at least 1 problems in the context of a table and picking people. So now let's talk about those 3 same concepts with rolling a die. Part A, if a 20-sided die is rolled, what's the probability of getting a number bigger than 8 or a multiple of 6? When I roll this dice, what are all the numbers I can get? I can get a 1, 2, 3, 4, all the way up to 20, because it's a 20-sided die. And in this problem, I'm talking about numbers bigger than 8. Let me circle the numbers bigger than 8. So bigger than 8 means you don't include 8. So bigger than 8 will be 9, 10, 11, 12, all the way up to 20. All of the circled numbers are bigger than 8. And then I'm also talking about multiples of 6. This means count by 6. Let me put boxes around those. Multiple of 6 would be 6. Plus 6 again would be 12. Plus 6 again would be 18. Okay. Probability of getting a number bigger than 8, or, keyword here is or. Bottom is going to be all different numbers I can get. So how many different numbers can I get? 20. For the top, I want bigger than 8 or multiple of 6. So or means, remember, you're going to take the two sets, combine them, and get a bigger set. In other words, I want all of the boxes together with all of the circles. In other words, I want any number that's in red. How many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Part B. If a 20-sided dice rolled, what's the probability of getting a number bigger than 8 and, keyword here is and, a multiple of 6? Bottom here is going to be all the total. So how many numbers are there total? 20. The top and means, remember, at the same time. So I want the numbers bigger than 8 that are at the same time multiples of 6. I want the numbers that are circled and at the same time boxed. Which numbers are circled and at the same time boxed? 12, 18. So there's 2 of them. Part C. If a 20-sided dice rolled, what's the probability of getting a number bigger than 8 given, keyword here is given, that the number is a multiple of 6? So the word given tells me that this is a conditional probability. And for conditional probabilities, I do recommend using the notation. So I'm looking for bigger than 8, given multiple of 6. Anytime you have a conditional probability, you should focus on some numbers. So what should we focus on? You should focus on a given part, which is the second part, multiples of 6. For the top and the bottom. So focusing on just the multiples of 6, which are the boxes, how many are there total? 3. Okay, so that's the total for the bottom. And then still just focusing on multiples of 6, how many are bigger than 8? So just the multiples of 6, or just the boxes, how many are bigger than 8? Those 2. Part D. If a 20-sided dice rolled, what's the probability of getting a multiple of 6 given? Once again, I see the word given. This is going to be conditional probability, given that the number is bigger than 8. So in symbols, I'm looking for multiple of 6, given bigger than 8. Because it's conditional probability, I should be focusing on some numbers. What should I focus on? You should be focusing on the given part, which is the second part. The numbers are bigger than 8. For the top and the bottom. Right, so focusing just on the numbers bigger than 8, how many are there total? These are the circles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, there's 12 total. That's my bottom number. And then still focusing on the numbers bigger than 8, how many are multiples of 6? So focusing just on the circles, how many are multiples of 6? Those 2? So 2. Part E. If 2 20-sided dice are rolled, what's the probability that both are bigger than 8? So we're talking about 2 now. I should have 2 fractions. And both of these I want bigger than 8. Bigger 8. Bigger 8. Okay, first fraction, the bottom, how many are there total? 20. And how many are bigger than 8? These are the circles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12. For the second fraction, this is where dice differ from the people and the table. right? When in the for the table example, when we're picking people, when I pick the first person, I'm not picking that same person again for the second slot, and that's why we have to reduce by 1. For dice, though, when I roll a dice, for the second time I roll a dice, I can still get all 20 numbers again, right? Any of the 20 numbers. So for when you roll dice multiple times, you don't reduce. Okay, so that means that for the second dice, I should have the full 20. And for the top, bigger than 8, because no matter what I picked for the first slot, when I roll a dice, it just resets itself, and you have the full count for the second slot. So for the second slot, bigger than 8, I should still have the full 12. Okay, and that's the key difference between dice and the table example where we're picking people. Part F, if two 20-sided dice are rolled, what's the probability that the first row is bigger than 8 and the second row is a multiple of 6? 2 dice again, that's 2 fractions. First one I want to be bigger than 8. Second one, multiple of 6. First fraction, the bottom is going to be everything. So the total, how many numbers are there total? There's 20. How many are bigger than 8? Bigger than 8 are the circles. I think we counted already. That was 12. Yeah, 12. And then again, for dice, you don't reduce. So the second fraction will be, the bottom will be full 20. Multiples of 6. These are my boxes. 3. And I don't have to think about reducing at all, so it's the full 3. Part G. If two 20-sided dice are rolled, what's the probability that at least one number is a multiple of 6? Okay, keyword here is at least 1. Okay, so we're looking for at least 1 multiple of 6. And the way we do at least 1 is 1 minus the probability none. So none multiple of 6. How many fractions do I need? We're talking about 2 dice, so 2 fractions. So rolling 2 dice, and I want none of them to be a multiple of 6. So what does that mean? So none of them multiple of 6 means not multiple of 6, not multiple of 6. So once again, even though we're looking for multiple of 6, because we're doing it using complements, the fraction should be not multiple of 6, not multiple of 6. First fraction, the bottom is going to be the total, which is 20. Second fraction, since dice you don't reduce, it's going to still be 20. Up top, how many are not multiple of 6? So these are the boxes. So how many are not boxes? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So 17 not multiple of 6s. And then for the second one, you should still have the full 17 because we're not reducing. Now let's talk about cards. Part A. If a card is selected from a standard deck of cards, what's the probability of getting a face card or a heart? Keyword I see here is the word or. For the bottom, how many cards are there total? There's 52. And the word or means I want all the face cards combined with all the hearts. So all the face cards, which would be the last 3 columns. So that's, what is that? 1, 2, 3. Times 4. So that's 12 face cards combined with the hearts. But I don't want to count these hearts twice, the J, Q, K hearts. So it's these 12 plus 1 through 10 hearts. That's 22 total. Part B. If a card is selected from a standard deck of cards, what's the probability of getting a face card and a red card? Keyword I see here is and. The bottom, how many cards are total? 52. Okay, and remember means at the same time, so I want the face cards that are at the same time red. Face cards that are at the same time red. In other words, red face cards. 6. So JQK hearts, JQK diamonds. 6. Part C. If a card is selected from a standard deck of cards, what's the probability of getting a face card given, keyword here is given, that the card is a red card, right? So this is conditional probability. I'm going to use notation here. I'm looking for face given red. Conditional probability means that I'm going to focus on certain cards. What am I focusing on? So you're focusing on a given part, which is the second part, the red. So we're going to focus on red for the top and the bottom. Let's start with the bottom. So focusing just on the red, how many are there total? So just the red cards, which is the bottom 2 rows. There's 13 in each row, which means there's 26 red cards total. And then for the top, still focusing on just the red cards, how many are face? So just the red cards, how many are face? Jack, Queen, King, hearts, Jack, Queen, King, diamonds. 6. Part D. If a card is selected from a standard deck of cards, what's the probability of getting a heart given that the card is a face card? Given, this is conditional probability. I'm going to write symbols. I want heart given face. Right? Conditional probability, I should be focusing on certain cards. What am I focusing on? So the given part, which is usually the second part, so I'm focusing on face for both the top and the bottom. Okay, let's start with the bottom here. Focusing just on the face cards, how many are there total? So just the face cards. Just the face cards would be Jack, Queen, King in each row. So that's Jack, Queen, King. That's 3 times 4 rows. 3 times 4 is 12. There's 12 face cards total. And then for the top, focusing just on the face cards, how many are heart? So just the face cards, how many are heart? Jack, Queen, King, hearts. 3. Part E. If 3 cards are selected from a standard deck of cards, what's the probability that the first card is a king of clubs, the second card is a club, the third card is a black card? Okay, so 3 cards, 3 fractions. And let me write the first card I want to be king clubs. So I'll write K club. Second club. Third black card. All right, so let's start with the first fraction. First fraction, bottom's going to be the total. And then how many are king clubs? First row here is clubs, king. That's it, just 1. Second fraction. Now, for cards, I'm picking a card, and then I'm picking another card, and then I'm picking another card. That's what it means to pick 3 cards. I'm picking a card, I'm not putting it back, I'm picking another card. So for cards, because I'm not putting it back, I should have 1 less card. So for the bottom here, I should be down to 51. And then for the same reason, for the third fraction, I should be down to 50. So for cards, you reduce. For the table, you reduce. The only one where you don't reduce is the 20-sided die, the dice. Okay? All right. Second fraction, I just want club. So club would be first row. How many are there total? First row would be 13 total, but you do have to think about whether you have to reduce or not. So total is 13, but have you used any clubs yet? Yes. So you do have to reduce by 1. We're down to 12. Third blank. Black. How many cards are black? So blacks would be first 2 rows. So each row is 13. That's 26 total. And now you have to think, do you have to reduce? Have you used any black cards yet? You use a king club. King club is black. Second blank, use a club, which is also black. So you actually have used two black cards already, which means you have to reduce by 2. So the total was 26 total. You have to reduce by 2, which means you're down to 24. Part F. If 3 cards are selected from a standard deck of cards, what's the probability that the first card is a red face card, second card is a black card, third card is a red card? Okay, 3 cards. First one, I want to be red face card, so red face. Second card, black. And third card, red card. Okay, first fraction, the bottom, total. How many cards total? 52. And then cards, you reduce. So we're down to 51 for the second fraction, and then 50 for the third fraction. First fraction, for the top, how many red face cards? Red face, Jack, Queen, King hearts, Jack, Queen, King diamonds. 6 red face cards. Second blank, black cards. Black cards would be top 2 rows. Top 2 rows would be 26 total. Do you have to reduce? Have you used any black cards yet? No, right? First card was red. So we haven't used any black cards yet. So we have the full 26. Last blank, red cards. So red cards would be the bottom 2 rows, which would be 26 total. But then you have to ask yourself, have you used any red cards yet? Yes, right? The first card was red. So we do have to reduce by 1 card. So we're down to 25. So make sure you understand why in part E, we reduced by 2. And that's because the first 2 slots were both black cards, right? King clubs, club, both black cards. Whereas in part F, we reduced by 1 because we only used 1 red card. G. If 3 cards are selected from standard deck of cards, what's the probability that at least 1 card is heart? Okay, keyword, at least 1. So I want at least 1 heart. And the way you deal with at least 1 is you do 1 minus none. All right, so it's going to be 1 minus, and then decide how many fractions you need. We're talking about 3 cards, so 3 fractions. And then for each of these 3 fractions, what does it mean for none of them to be heart? So none of them heart means not heart, not heart, not heart. Okay, so once again, even though we're looking for at least 1 heart, because we're doing complement, you look for not heart, not heart, not heart. All right, first fraction, the bottom is going to be the total. How many cards total? That's 52. And then we're talking about cards here, so you do reduce. So you should be reducing for the cards examples and also the table where we're talking about people. First blank, how many not hearts? Not heart would be first row, second row, third row. So first row, second row, third row. That's 13 cards per row, so 13 and then 3 rows. So 13 times 3, 39. Next one, I want to be another not heart. Because we used one not heart already, we do have to reduce. So we're down to 38 and then 37. And that's it for today's lecture. Have a great day. Talk to you guys later.